Today's video is about Le Chatelier's principle. So this is a principle that was developed by this guy a long time ago, named Le Chatelier, obviously, where he just summarized how we can predict responses to changes in an equilibrium system. Some of this we've already done, a little bit of review, but some of it we haven't thought about. This is a direct statement of Le Chatelier's principle. If a system at equilibrium is stressed, the system will respond by shifting in the direction that reestablishes equilibrium. So in other words, the reaction will either go in the forward direction or the backward direction in a way that will help it get back to where equilibrium conditions were. One of the stresses that can cause a shift in equilibrium is changing concentrations. So for example, let's say we have this reaction where 2HI is decomposing into H2 and I2. And let's say that at equilibrium, concentration of H2 and concentration of I2 are both 0.03, but concentration of HI is 0.24 at some temperature. First of all, let's figure out what is the value of Kc. Well, this isn't hard to do. Kc is just going to be concentration of H2 times concentration of I2. We've been doing this a bunch now, divided by concentration of HI. So that's going to be 0.030 squared divided by 0.240. And that's also going to be squared. I forgot to square that. And this ends up being 0.0156. Now, what would happen if, while this was at equilibrium, we added HI until the concentration of HI went up from 0.24 to 0.3? Let's look at it graphically. This is concentration versus time. If we started out initially with all HI, let's say, and no H2 and I2, we would decrease concentration of HI and increase the concentration of the H2 and I2 until we reached our equilibrium. So we're coasting along here at equilibrium, and then at this point we add some HI. So the concentration of HI is going to spike upwards, and then at this point let's calculate what is Q. So Q is going to be, this is still 0.030 for both H2 and I2, but now in the denominator we have 0.300 squared. So Q is now 0.010. But Kc, remember, was 0.0156. So what's happened is Q is now smaller than Kc. The only way we can get Q back to the size of Kc is if we reduce the denominator by using up some reactant and increase the numerator by creating some product. So that means this reaction is going to shift in the rightward direction and produce more product. Graphically, if we looked at that, what would happen is the concentration of H2 and I2 would increase, and the concentration of HI would go down. It will go down until they reestablish equilibrium. And when that's accomplished, we'll see that the concentration of HI is not as high as it was right after we added it, but it's still a little bit higher than it was before. There's a kind of an increase there. And H2 and I2 concentration have also increased. What would have happened if we had, instead of adding HI, we added H2? So if we're at our first equilibrium here, and then we suddenly increase the amount of H2, this is the H2 concentration line, then thinking about the fact that Q is concentration of H2 times concentration of I2 divided by concentration of HI squared, this makes the numerator too big. So that means Q is now going to be bigger than Kc. So in the opposite of the previous situation, we now need to make the numerator smaller, which means less products, and the denominator bigger, which means more reactants. So in this case, the reaction is going to shift back to the left. So that means we're going to consume some of the H2, and we're going to consume some I2. So this is H2, and that's I2. And as we do that, we're going to create more HI and then reestablish equilibrium at some point. Here's another question to ask. What would have happened if instead of adding something, we had removed something? Let's say we had removed HI. Let's think about what that would do to Q. Remember that Q is concentration of H2 times concentration of I2 divided by concentration of HI squared. So if we're removing some HI, we're making the denominator smaller. That makes Q bigger. So Q is now bigger than Kc. How are we going to make Q go down. We can do that by shifting the reaction to the left and producing more reactants, denominator, and taking away some products, numerator. So this shift occurs after a decrease in concentration of HI by creating more reactant from products. So that means the H2 and I2 concentrations are going to drop and the HI concentration is going to go up until we reestablish equilibrium. So concentration of H2 and concentration of I2 are going to go down. Concentration of HI goes down, it comes back up a little bit, but it still remains lower than it was before. So let's summarize. If you have a general reaction situation where reactants become products, in general, Q is going to be ratio of products over reactants. So if you have a situation where you add a reactant or remove a product, either of those is going to make Q smaller than K. And the reaction is going to shift to the right to increase the value of Q, making more product from some reactant. On the other hand, adding a product or removing a reactant is going to make Q too big. So the system is going to respond by shifting to the left, and what that does is use up some product and create some reactant, making the numerator smaller and the denominator bigger until you get back to equilibrium. Here's another stress that can occur. Changing volume by making the size of the container larger or smaller. So let's say we have this equilibrium set up. What would happen to Q if we decrease the volume? Let's define what QP is. QP is pressure of SO3 squared over pressure of SO2 squared times pressure of O2. But remember that P is equal to nRT divided by V. So this could be rewritten as number of moles of SO3 times RT over V squared, and that's squared, times number of moles of SO2 squared times RT over V squared, times the number of moles of O2 times RT over V, just raised to the 1 power. Now R and T are constants. We aren't changing T. R is always constant. And another thing that's true is we aren't changing the number of moles of anything here. We're just changing the volume. So we can think about QP then as being proportional to 1 over V squared over 1 over V cubed, or V cubed over V, or just V. So if we were to decrease the volume, decreasing the volume would make Q smaller. If Q is smaller, that means you need more product, less reactant, so that means this reaction is going to shift to the right. What would happen to Q if we increased volume? Well, if we increase the volume, since volume is proportional to Q, Q is going to increase. What happens when you have Q too big? You want to reduce the numerator and increase the denominator, which means you want the reaction to shift to the left. What about this one? What happens to Q if we increase volume? Well, here, QP is going to be equal to number of moles of H2 times R times T over V times number of moles of I2 times R times T over V divided by number of moles of HI times RT over V squared. Remember, R and T aren't changing, and the number of moles of anything isn't changing either. So that means that Q is proportional to 1 over V squared over 1 over V squared, which means it's proportional to a constant. So changing volume is not going to have any effect on Q. If we increase it or if we decrease it, there will be no shift in either direction because Q doesn't depend on volume in any way. Let's summarize this. Q is proportional to the number of moles of products divided by the number of moles of reactants, roughly, times RT over V raised to the change in the number of moles of gas from left to right. Because R and T and the number of moles of reactants and products are constant, the only thing this is going to depend on is changes of volume. So if the number of moles of gas on the left-hand side of the equation and the right-hand side of the equation are the same number, changing volume is not really a stress, and there's going to be no shift in the reaction. But if the number of moles of gas is not equal to 0, changing the volume is going to be a stress. Now, you can work this all out using this formulation, but it's easier to remember probably that if you decrease the volume, you're going to shift in the direction that makes less gas. So if the reactant side has fewer moles of gas than the product side, decreasing the volume, you're going to shift to the left-hand side, or vice versa. And if you increase the volume, you're going to shift in the direction that makes more gas. So going back to this previous equation, we can see that there's no difference. There's 2 moles of gas on the left-hand side and 2 moles of gas on the right-hand side, and that's why there's no shift. But if we go back to this reaction, this has got 3 moles of gas on the right and 2 moles of gas on the left. So if we decrease the volume here, we're going to move in the direction that has less gas, shift to the left. If we increase the volume, we're going to move in the direction that creates more gas, shift to the right. The third stress that we're going to look at is stress caused by changing temperature. Changing the temperature usually causes a shift. And this is not due to the fact that Q drifted from K, because our concentrations aren't changing. We're just changing the speeds of the particles by increasing the temperature. A way that we can make this prediction is thinking about energy as a product or reactant. So in this example, enthalpy change is positive. That means this is an endothermic reaction. So you could think about writing this as 57 kilojoules as a reactant almost, plus N2O4 gas in equilibrium with 2NO2 gas. So if the temperature increases, this system can react to that stress by using up the extra energy in the environment by shifting to the right, which is an energy input process because this is endothermic. On the other hand, if you put this in a low temperature environment, this system could release energy by shifting to the left. So in summary, we could say if the temperature is increased, the system is going to shift in the direction that uses up the excess energy. Or conversely, if the temperature is decreased, the system is going to shift to produce energy to make up for the lost energy from the low temperature environment. Because this shift is not due to a change in Q, as we've discussed, what's happening is Q isn't K anymore because K is the thing that changed. K changes with changing temperature. This is what the graph looks like. It's not linear. And when you finally linearize it, you find out that the natural log of K is proportional to 1 over the absolute temperature. This is a pattern that we've seen before. And like before, the slope has a meaning. The slope is the delta H for the process divided by R, and it's opposite, it's negative. So if you put this together, this is the equation. The natural log of K is equal to minus delta H naught over R times 1 over T plus a constant number. That's the vertical intercept. This is analogous to an equation that we saw before that relates rate constants and temperature. And it's also analogous to another equation called the Clausius-Clapeyron equation, which relates the pressure of a vapor to temperature. When we were discussing the gas laws in an earlier set of videos, we noticed that as the temperature increased, the vapor pressure, or the pressure of water, in a closed container would go up like this. Linearizing that gives you the natural log of vapor pressure and 1 over T also having this sort of a linear relationship. And once again, the slope has some meaning. That's called the Clausius-Clapeyron equation. These equations are not really part of the AP curriculum anymore, but it's kind of sad because I think it's very interesting to see that these same mathematical patterns show themselves in these fairly different physical phenomena.